My name is Bahjat Kawar, and today I will be presenting the stochastic image denoising by sampling from the Posterior distribution. So let's have a look at classical image denoising. We have an original clean image that we assume was contaminated by white additive Gaussian noise, and we put it through a denoiser, one that is based on a neural network, and we get this result. Should we be satisfied with this result? It looks a little blurry. If you look at the clouds, you don't see the fine details that were in the original image. Now, why is that? It's because most deep learning based denoisers today attempt to minimize some sort of distance between the reconstructed image and the original image. For example, most notably, the mean square error loss. Now, if we imagine that this is the image manifold, the manifold on which the natural images sit, and this is the noisy image we have as an input. This is the set of natural images that could explain the noisy image. This is an ill-posed problem. There are multiple solutions to it. The MMC results would just be the expected mean of these images, which in this case would sit outside the manifold. That's why we get a reconstructed image that is not visually pleasant. It is not of good perceptual quality. If you want a good perceptual quality denoiser, we need to output one of these images that are natural and could still pose a viable denoising results. What I just said has a more formal definition. It's called sampling from the posterior distribution. We want to sample from the distribution of clean images given the noisy image Y. How can we obtain such an algorithm? We use Elad dynamics that was introduced by Song and Hermon in 2019. This method samples from a prior distribution P of x, where x is a natural image, using this iterative equation that is based mostly on the score function, which is the gradient of the log of the probability, and it is approximated using an MMC denoiser. It also involves a stochastic element, which is zk, which is sampled in every iteration from a normal Gaussian distribution. Now, what happens here is that we consider a sequence of gradually less blurred priors. We start with a prior in step k that has a high sigma k, and we gradually go down and down to less and less noisy priors, less blurred priors. So we consider this blurred image manifold that starts white and then narrows down. This helps in a faster sampling performance in sampling from a prior distribution, and this is basically the core idea of Elad dynamics. Now, we want to sample from a posterior distribution, not a prior, so we just use the conditional score function, the gradient log of the posterior distribution. So we use the bias rule in order to obtain this function, and the first term here is just the regular score function that can still be approximated using a denoiser as before, and we have this new term. Let's examine it for a minute. We have y, which has the original noise in the measurements, which is of standard deviation sigma 0, and we have xk, which is the running parameter that we run with during the iterative algorithm. It has a synthetic noise that we control of standard deviation sigma k, which starts very high, like close to sigma 0, and ends up being very close to 0, sigma l. Now, our core idea here is that we want to recover a sequence of gradually less noisy images xk, starting from y and going down to near x, where the noise is assumed to be a portion of the noise in y. That means we take y, and we gradually, during this algorithm, we peel more and more layers of noise from y. So this means that the residual between y and xk is actually just the noise, and it is independent of the noise that it is built upon. It is independent of the noise in xk, it is independent of xk itself. And its variance is just the difference in variances. This leads us to the following. This gradient log term, because xk is a known quantity, we can substitute it here, and because this difference is independent of xk, we can remove the dependence on xk, and we get the gradient log of the Gaussian distribution, which is a function that we can easily calculate, and we get this following result. And if we go back to our base rule, we get this term for the conditional score function, which involves the first term, which again can be approximated using a denoiser, and the second term, which can be easily calculated as we go along the iterative algorithm. So we plug in this conditional score function into the longevity dynamics algorithm, and we try to denoise. Start from a noisy image, in this case with a standard deviation of 150, and then the algorithm gradually peels off this noise. It gradually removes this noise until we get a high perceptual quality denoising result. What you see here is the intermediate steps of our algorithm. Here we can see more results of our algorithm on images from Celebay and Elsan. As you can see, our algorithm in comparison to an MMSE on an MMSE denoiser gives much better high perceptual quality. If you look at the hair in the Celebay image, you can see that it is very, very blurry in the MMSE result because it is the expected mean. And in our algorithm, it is just a sample from the posterior with high perceptual quality. Here are more results on FFHQ in a higher dimension. And we do mention that our algorithm is stochastic. It gives a sample from the posterior distribution. That means it can produce multiple outputs for the same input. Here, the first row is the input, and the rest of the rows are just different outputs of our algorithm. You can see the difference in the fine details, such as the hair and the eyes of each of these faces. Now, we also expand our algorithm to image inpainting, where we observe a noisy version of the image with missing areas, and we attempt to recover the whole original image. We tackle this problem similarly to before using annealed longevity dynamics. We derive the conditional score function for this specific problem, and then we sample in the same way. The full details of the derivation are available in our paper. And here are some results. The first row here shows the clean original images, and the second row shows the observed noisy images with the missing parts. And in the two following rows, you can see two samples of our algorithm. You can see that since the mouth area is covered in the observation, we, for example, do not know if the mouth is open or closed. We do not know if this woman has lipstick or not. So some samples might show these features and some might show different features, which shows a great uncertainty in the image inpainting problem. The image inpainting also has a practical use of removing text overlay from the top of an image, as you can see here. And more results are available in our paper. Thank you for listening to this talk. If you have any questions, please ask.